Can you hear me? Okay. Okay, thank you. So first of all, it's my pleasure to thank the organizers for this opportunity to present my results at this nice conference. So what I'm going to present here is very much a work in progress, so this talk will be short and quite non-technical. I'll present an infinite hierarchy of non-local conservation laws for vacuum anti-self-dual Einstein equations with non-vanishing cosmological constants. So, okay, so the most important point we need to begin with is the fact that this special case of the Einstein equations, vacuum anti-self-dual Einstein equations with non-vanishing cosmological constants, represent an integrable system. Just very briefly, let me recall that integrable systems are such nonlinear systems which combine in a certain nice way nonlinearity and tractability, and the latter means many nice features like existence of infinitely many conservation laws, large symmetry algebras, and also typically infinitely many exact solutions. And another key feature of the integrable systems is that they always arise as compatibility conditions for certain linear overdetermined systems, and these linear systems are then known as Lex pairs. Also, let me say that, of course, the history of the relationship among integrable systems and general relativity is very rich and beautiful. Einstein equations admit plenty of reductions which happen to be integrable systems. Perhaps the best known example is the Ernst equation, but today we shall deal with something different. So it turns out that when we have anti-self-dual solutions of vacuum Einstein equations with non-zero cosmological constants, then we can locally write the metric in this form. Capital lambda is just a good old cosmological constant. Okay, u is a real function of these four coordinates. Bar, as usual, indicates complex conjugation, and subscripts refer to partial derivatives. So this guy u for this particular metric is known as the Perranoski function. Okay, let me also point out that so in this talk we shall assume that the cosmological constant is always non-zero, because going to the limit of lambda equals 0 is quite tricky matter, and not really possible when we use this explicit form for the metric. Okay, now when we write down the Einstein equations proper, that is that the Ricci tensor of our metric equals to lambda times our metric, we end up with the following equation, known as the Perranoski equation. Just as a small aside, let me remark that it has an interesting behavior under reductions. So if we try to impose some simplest reductions, just drop the dependence of u on one of the variables, we either get a trivial identity, or in the second case, when we drop the dependence on z or z bar, we end up with this equation, which is easily integrated. Okay, but a far more important fact is that the Perranoski equation admits a Lex pair. That is, it can be written as a commutativity condition for a certain pair of scalar linear differential operators, which have the following general form. So here we use, of course, the Einstein summation convention. That J are just our coordinates, Z bar and W bar, and Xi is essentially an additional independent variable, the so-called variable spectral parameter. And it is assumed here that our Perranoski function U is independent of Xi. So these L's form what is called a non-isospectral Lex pair. Now more explicitly, the L's have the following form, and Q we have here. So they are fairly complicated guys, and it can be readily checked that indeed when we write down their commutator, the condition of vanishing of this commutator will give us precisely the Perranoski equation. Okay, now we can if we look at these guys, we see that they are not really homogeneous. So this guy with respect to Xi, namely this guy L2 in this last term involves the terms which are quadratic in Xi and also the terms which are linear in Xi. And for reasons we'll get to in a moment, it's not quite convenient, but fortunately we can solve this problem by passing from Xi to another variable P defined by this formula, and then our Lex operators small l alpha go into the new operators L capital alpha, which are written here. And now we see that they are kind of homogeneous with respect to P. So they have okay. So at each derivation, like the Z or the dW or whatever, we always have the terms with just one power of P, either zero order or linear in P or quadratic in P. Okay. Now, in order to deliver what was promised in the title of the talk, the conservation laws for the Perranoski equation, let's do the following trick, which is actually quite well known from the literature. Let's substitute this formal Taylor expansion into these equations, well known as the Lex equations. Okay. Now, if we do that and assume that chi depends on P as well as on our coordinates Z bar and W bar, we immediately see that chi 0, the first term of the expansion, depends only on W bar and Z bar. And at the next order in P, we get the following pair of equations for chi 1, which can be sort of integrated, and the result is here. But sort of, because to write down this formula, we need to introduce the nonlocal variable omega 1, defined by this pair of relations. So this guy omega 1 is basically a potential for this local conservation law of the Perranoski equation. And also, actually, the introduction of this variable W1 allows us to write the Lex operators L capital alpha in a somewhat simpler form, namely like this. And moreover, now we readily see that our L's can be written in the following nice form using just a single operator, capital A, which is written here. Okay. Now, if we make use of this information and proceed with our formal Taylor expansion for chi and get to the higher orders, we get the following recursion relations. So chi k plus 1 for each of these values of k is defined by this pair of formulas. Mathematicians tend to call such sets of relations differential covering. So we can say that we have an infinite dimensional differential covering over the Perranoski equation. And this covering involves these relations and also the relations which define omega 1. Okay. And now, now getting the conservation laws is quite straightforward. So we can just write down the consistency condition, saying that the second mixed derivative of k plus 1 with respect to w and z does not depend on the order in which the derivatives are computed. So we end up with the following set of relations, and these are precisely the non-local conservation laws for the Perranoski equation, as I promised. So we have indeed an infinite hierarchy of non-local conservation laws for the Perranoski equation. Okay. So some of you might wonder why these conservation laws need to be non-local. What happens? It turns out that this is actually a very typical feature of integrable systems in 4 independent variables. So the very same phenomenon occurs, for instance, if we try to construct a hierarchy of conservation laws, say for anti-self-dual Young-Mills equations, which are kind of prototypic integrable models in 4 independent variables. One will immediately see that one ends up very quickly with non-local conservation laws rather than local ones. And of course, these conservation laws, at least I hope so, should have a number of applications, which I'm still intend to explore. One such application would be to construct symmetries for the Perranoski equation. Because, again, as it was already mentioned at the beginning, one characteristic feature of integrable models is that they have infinite hierarchies of symmetries, and again, for integrable models in 4 independent variables, it turns out that these infinite hierarchies of symmetries are non-local. Okay, so to sum up, I've shown you today an infinite hierarchy of non-local conservation laws for the Perranoski equation. Okay, at this point, I should perhaps make a brief historical comment. So, the Perranoski equation was introduced quite naturally by Perranoski back in 1983, and also it turns out that this equation can be related to a certain twistor space, and this was exploited by Hegner in 2012, who has produced the Lex pair for the Perranoski equation I've shown you at the beginning, the one with small l's. Okay, and as I have told, these conservation laws, at least in principle, have plenty of possible applications, and one of them, which is now my work in progress, is to construct non-local symmetries for the Perranoski equation. And of course, which is trickier, but perhaps I'll be able to do some of that. It would be nice to try to figure out whether any of these non-local conservation laws or non-local symmetries can admit some sort of physical interpretation and perhaps employed for the construction of new exact solutions for the Perranoski equation, and therefore for anti-self-dual vacuum Einstein equations with non-zero cosmological constant. Well, that's it. I thank you very much for your attention. Well, thank you. That's an excellent question. So I should refer you for this to the paper of Hegner of 2012. So here he gives a very nice survey of twistorial approach to the Perranoski equation, but also I should mention that to a large chunk of work in this direction was done some 35 years ago by Richard Ward. So I think his paper in Communications in Mathematical Physics, which initiated the study of relationship among self-dual gravity with non-zero cosmological constant and the twistor theory.